single day, when you double it every single day, it starts off really slow, right? After 1 week, I still only have 64 cents. After 2 weeks, okay, I got $82. It's still kind of low. But what happens in the third week?
You go from $81 to $10,000 and then to 1.3 mil.
Yeah. We jump from $81 to $10,000. And that is the power of doubling, like a pattern where you're multiplying by a number each and every time. That's the power of it. You end up going from one day to the next. You can literally go from just under $100 to over $10,000, and then wait a week and a half, and all of a sudden you're at $10 million.
Do we get $10 million?
Elon Musk will give you 10 million. I'm not going to give you $10 million, but maybe Elon, if you go knock on his door and see what he says, maybe he will.
Okay.
I was actually thinking from this because when I was looking at this chart, I was thinking it might be a trick question from this.
Yeah, right? Because what is it? Okay, why does your brain trick you into thinking that payment plan number 1 is going to be better?
Because Elon
your
Musk
brain
says
doesn't automatically calculate exponent functions. It just big numbers need big money.
Right. And Dejuan, what were you going to say?
that pretty much 32,300 times 31 is going to be pretty much just like a solid 1 mil. But if you keep multiplying like a penny over time, it's probably going to increase.
Right. Over time. That's the key word. You got to wait your time. Eventually, it's going to make big gains. And that's how we end up with $10 million. So that's actually what we're going to be talking about a lot today. We're going to be learning about exponential functions. We've been talking about exponents a lot. We did a lot of stuff last week about adding, multiplying, subtracting exponents and turning them into radicals and all those things. Well, now we're actually going to put those exponents into action, and we're going to be talking about exponential functions. Because what's really happening here is, because you're multiplying, you're doubling each and every time, what exponent goes with the word double? What's my exponent?
2.
I'm doubling something, yeah. I'm taking it to the power of 2, right? So what I'm really doing is I'm growing this function exponentially. And we know that with exponents, after a while, those numbers become much larger and much larger and much larger at a very rapid pace. So that is kind of the basis of what we're doing today. And what I wanted to also look at right off the bat is thinking about this scenario, right? The difference between $32,300 each day versus a penny doubled every day. What that looks like on a graph is like this. So before we kind of read everything on this page, I just want you guys to look and notice the differences between the green line and the blue one. So the green one is representing payment plan number 1. And then the blue one is payment plan number 2. Okay. And what type of line or what type of graph is my green graph? We know what this is called. What's this called?
A function. A linear function.
Good. That one is linear. It's a linear function because it has a straight line. And what do we know about linear functions? Like, how do they grow?
In a line.
In a line. There's a key word we've talked about in the past. Starts with a C.
Constant rate.
Yeah, you got it, Ilse. This has a constant rate. Constant rate is when you add the same amount every day. So with payment plan number 1, Elon Musk is going to give me $32,300 on day 1, $32,300 on day 2, on day 3. My bank account is going to add that amount every day. I'm adding. But with payment plan number 2, do I have a constant rate?
No.
No, no constant rate. No constant rate. Instead, what's happening is we're multiplying. So I'm not adding the same amount. Instead, I'm taking what I had the day before and I'm multiplying it by 2. So now can I get a volunteer to read what exactly is an exponential function? And while my volunteer is reading, I would like you guys to go ahead and start writing that down. So who can read?
An exponential function is a function that grows or decays following a constant factor. Each successive output value of the function is multiplied by the constant factor to obtain the next output value.
Perfect. Thank you, Philip. And so go ahead and just write that down. Yes, write it in your notebook. That is the definition of an exponential function. And we're going to talk about these patterns. So like we're going to talk about what is a constant factor. We'll talk about how it multiplies and how it grows. But for now, just go ahead and write it down. All right. So kind of like we were noticing before, the constant factor is what makes exponential functions grow so quickly, because even if you start off with pennies, even if you start off with a tiny, tiny amount, what happens over time when you compare these two functions?
It grows.
It grows. And what happened with the blue and the green line after 25-ish days?
They meet up.
Right, they meet up. And from that point on, which function is always going to be much bigger? Which one wins in the end?
The first one.
Right. So it's what's super important to notice is that even when you start off with a very small amount, even when it seems like that function is just not going to get you anywhere, eventually, the exponential function will win. It's going to exceed the linear function. No matter what. If you have even the best payment plan in the world, if you're making $1 million every day from Elon Musk, that exponential function, even when you start from pennies, is always going to win, no matter what. Sometimes it just takes a while to get there. But no matter what, exponential functions always beat linear functions. They always exceed linear functions. So any questions on so far the difference between exponential versus linear? Okay, awesome. All right, so now let's actually kind of write down a little bit more of organized notes. So on the next page, I'm just going to compare. Once again, we're just going to summarize everything we just talked about. But I also want to do one more thing. Does anybody remember what the equation for a linear function is? Y equals what?
MXB.
Plus B.
MX plus B.
Good. Mx plus b. So I just want to notice the differences between just the equation for a linear function versus an exponential function. Where is the x located for an exponential function?
On the next of the B. Well, it's the power.
Yeah, it's the power. So it is the exponent. That's why it's called an exponential function. So the x is in the exponent. Whereas on a linear function, it's just hanging out with all the other numbers. It's not an exponent. So that's one thing I definitely want to talk about. And now let's just talk about the differences. So like we already said, linear functions grow at a constant rate of change. And that rate of change, we talked about what operation is happening from one number to the next. Am I adding, subtracting, multiplying? What's happening? With a linear function. So remember, think about option payment plan number 1. Every day, what's happening?
Adding.
Good, I'm adding. So linear functions, they grow at a constant rate of change, which means you are adding or subtracting. Sometimes they go down. We add or subtract to get the next value. That's the pattern. Now, on the other hand, exponential functions do not grow at a constant rate. Instead, which operation happens? What's the pattern?
You multiply.
Multiply.
Multiplication, yeah. So we multiply to get to the next value. And what that's called, we kind of wrote it down on the previous slide. This is called the factor. Sorry, I wrote it down over here. This is the constant factor, or sometimes it's called the growth rate. The growth rate. All right. Whereas for linear functions, we call that the slope. So linear functions have a slope, exponential functions have a growth rate. With Elon Musk, he was paying me payment plan number 2 multiplied by 2 every day. So the growth rate was 2 because that was what you multiplied by each day to get the next number. So this is kind of like a big summary of the difference. Does anybody have any questions on linear versus exponential?
No, but can you go back to the previous slide? I'm almost finished with the notes. I just didn't get to finish it.
Okay, I'll stay on this slide for like 30 more seconds, then I'll flip back for 30 seconds, and then we'll move on. All right, going back for 30 more seconds. And all right, let's go ahead and move on and we'll kind of get more into it. So the thing is, exponential functions and linear functions, but exponential functions a little bit more, they exist in our day-to-day lives. Like we already kind of gave a silly example with Elon Musk, but can anybody think about a more real-world example of something that grows exponentially?
An investment, like when you put something in a savings account.
Yes, exactly. So a lot of times money in general, money happens to grow exponentially. So investments, investing in the stock market, putting things into a savings account or some sort of like retirement account, that's definitely exponential growth. Can anyone think of anything else? I'll give you guys a hint. There's one very, very relevant, real world, like happening today thing that is everywhere, all around us.
Oh,
Coronavirus. Yes, ma'am. All right. So think about what happened back in March, almost a year ago, right? We were living our lives like normal, no masks, no social distancing, nothing crazy. And we kind of heard about the virus, like it was in China, it was in Asia, it was in Italy, but it wasn't here yet. And then we started hearing on the news, like, oh, okay, there's like 5 cases in New York City, 10 cases in California. Then Florida got its first case. Then all of a sudden there were like 20 cases and then like 100 cases. And then what happened? Like seemingly from one week to the next, what happened?
we reached 1,000 and then 100,000.
Increasing.
Yeah. And we had to shut it all down, right? So it just happened really, really suddenly. And why exactly does that happen? So let's actually talk about COVID-19 and talk about why the virus spreads exponentially. Let's say this is poor little Timmy. Timmy is infected. And by the way, this happens with all viruses. This is not just for COVID, but it is obviously really relevant with COVID. So Timmy gets the virus, but he doesn't know he has it because something that is very unique about coronavirus is that you don't start showing symptoms right away, right? So he doesn't know he has it, and he goes to school, and he spreads it to his 2 friends. Luckily, it's only 2 friends, not more. But then
So
those...
can his friends' names be Aristotle and Galileo?
No, I'm not gonna give, because then after a while, if I start naming everybody, it's gonna get crazy. Well, his 2 friends go home. They don't know they're infected. They bring it home, and their parents get it. So there's mom and dad. Okay. So it's been 3 days. I started with just 1 person. Now I'm up to 4. So far is not too terrible, right? So, but it keeps going. And this is only if we're lucky. This is only in a perfect world where you only end up infecting 2 other people, but we know that that's not always true. You might spread it to way more people. Okay, so now mom and dad go to work, and each of them makes 2 people from work get sick. So now I've got 8, right? And it's only been how many days?
1 day.
Think of each event is 1 day. So day 1, day 2, day 3, day 4.
It's only been 4 days.
It's been 4 days. What's going to happen on day 8? Day 5? How many people are infected on day 5?
16.
16. Because each of those 8 people got 2 more. Day 6, how many people?
2.
32.
And then 64.
And then 64, and then
108.
108. And
No,
before you know it, after about 2 weeks, if I do this for 14 days, this was day 6, day 7, day 8, day 9, about 14 days later, does anyone know how many people are going to be infected?
Miss, I meant for it to be 112, 108.
Oh, sorry. Yeah, I wrote it down wrong. 64 times 2 is 128. And then 256. And then before you know it, you've got about over 1,000 people, over 2,000 people after just about 2 weeks. So long story short, exponential growth, if we're talking money, if I'm investing in a bank account or a stock market and it grows exponentially, that's awesome and that's great. But on the flip side of things, when exponential growth happens to something that is bad, like a virus or bacteria or something else like that, that is bad news. That is bad news, because often what happens is it grows so quickly and it spreads so quickly that people and also governments are not able to deal with it, and they're not able to handle it in time. And that's what happened here, as well as pretty much everywhere else in the world. So looking at a graph, this is actual data. I got this from the BBC, which is an international news source. But here's a graph of
BBC is actually just British.
It's, yeah, British Broadcasting something. This is an actual graph with actual data from the United States of the number of daily cases of COVID. So I want us to actually look at this graph and let's think about, where do we see exponential growth? Where is exponential growth happening?
March to April.
March to April. So around here. Exponential growth. And what was happening from March to April? Here and in other parts of the US.
Nobody knew what the
Right. Lack of understanding, lack of education, lack of research. We didn't really know how the virus was spreading. Most people used to think that it was only from surfaces. So if you guys remember, at first, everyone was like, oh, wash your hands, wash your hands, wash your hands. But they didn't talk about masks or the fact that you can spread it just by even talking, right? So we didn't know much about the virus. A lot of places didn't shut down fast enough. A lot of people just didn't care because they didn't realize how deadly it was. There was just a lot of issues where people didn't notice, and they continued to spread it because they weren't taking the proper precautions. Well, what happens then from April to June? Is that exponential anymore?
No, it's a decline because people were aware and started taking precautions.
People started taking precautions. And rather than exponential, would you guys think that this follows a slightly more constant rate? It's not
Yes.
perfect, but it is a little bit more. Yeah. So this is a little bit more like linear, a linear decrease. And then what starts to happen in July? What's starting to happen there? Up again, right? And in fact, I didn't show the rest of this because this data only went up until July, but if you actually look at a graph, this is where we're at right now. Something like that. So what's going on here? Why do we think this went back to exponential?
Because people started opening places up.
Yeah, they open schools.
Opening of all sorts of, not just schools, right? Malls, bars, restaurants. And in general, I think we got like a false sense of security, you know? We saw that decrease and we were like, oh, this is almost over, it's fine. And it really wasn't fine. So a lot of people just kind of got used to it and decided to live their life as if it didn't really matter. So that is why we kind of fell back into the same sort of pattern, because we stopped, not everybody obviously, but a lot of people stopped really caring about it and stopped taking those precautions that we had been really, remember how intense people were back in like April about it? Now a lot of people are way more relaxed and don't really care as much. So, you know, this is what's going on. Now, what do you think? Hopefully, why do you think we were on a current decline? Because we are. It is getting slightly better every day, but why?
Because the weather sucks.
What does that have? Actually, no, what does that have to do with it?
People are going outside then.
Mm-hmm. And what are some good things that are happening that are starting to bring it down? Good. Increased social distancing. What else?
People's in the stores know what to do now, so they have like prepared, like they clean everything. They make sure that everything is clean and stuff.
Yeah.
And plus, you can't go into any stores without a mask. So
yes, much stricter rules. Good. All of those things, and hopefully we'll see continual decrease because of the vaccines that are starting to be able to be accessed and all of those things. So obviously, it took a really long time for us to get here, but it's hard to beat exponential growth. exponential growth happens so quickly and so intensely that it's really hard to like shut it down. It's really hard to bring it back down. So, you know, everything that you can do personally obviously is very important and in your day-to-day life. But I'm hoping, I'm crossing my fingers that we continue to see that decline. So long story short, exponential functions are definitely all around us. They happen in the real world all the time. And now that you know how powerful they can be, you can be more aware. And you might start to notice them in different ways in your life. All right, back to a little bit more normal math. But, you know, on a test, a lot of times they're going to show you different real world scenarios. And you have to figure out if that scenario is going to be an exponential function or if it's going to be a linear function. So let's go ahead and just take a look at example number 1. A student wrote the 5 different situations that are shown in the answer choices below. Select all of the situations that could be modeled by an exponential equation. Now, what I want you guys to do right now is just start looking at the choices, and if you would like to, go ahead and annotate on the screen, circle or underline any key words or key things. Doesn't even have to be a word, it could be number or a symbol or something like that, that might help us to figure out if it's going to be exponential or linear. So go ahead and annotate on the screen. Good. Seconds squared. That's a good keyword. And anybody can annotate. Go ahead and do it. Go ahead and just circle or underline any keywords that you notice. And matter of fact, I just made it anonymous so people won't know it was you. So go ahead and annotate. No names will be attached. That's all the keywords in this whole entire thing? No more keywords?
Oh, Cole, you annotate by at the top of the screen. There's a it it says you are viewing Miss Lopez's screen. So you click view options, then it'll be a drop down bar, and you'll see annotate. Just click it, and you'll be able to draw on the screen.
Perfect. Yeah, it's on the little view options up top. Good. 2 feet per year. Good. 62 miles per hour. Beautiful. 4% per year. And anything in E? 45% every 10 minutes. And we'll go on to example 2 in just a moment. So I saw a couple people were annotating for example 2. Just give it a moment and we'll get to those in a minute. Okay, so now we got to figure something out because there's a difference. We know that linear has a constant rate. And what operation goes with linear?
Addition.
Addition. So linear, we're adding a certain amount every day. Exponential has not a constant rate, but it has a growth rate. And what operation goes with that?
Multiplication.
Multiplication. So that's what we got to figure out the difference. So let's start with the first one. The Barton family is driving at a rate of 62 miles per hour. So is that a rate, am I adding 62 miles every hour or am I multiplying by 62 miles every hour?
Adding. Also, is this by Bart? Is this the Hawkeye family?
I don't know anything about that, so maybe. But we are adding, exactly. So I do 62 miles the first hour, Then I add another 62 miles. Now I have 124 miles. Every hour you're adding 62 miles. So this is linear. Okay, I'm gonna skip B because it has a percentage and that's gonna be something interesting. So I'm gonna skip it for now. We'll come back to it. Let's go to C. A tree was 10 feet tall when purchased. It is growing at a rate of 2 feet per year. So is that tree going to multiply by 2 every year or just add 2 feet to its height every year?
Add.
Add.
Add again. So this is linear. Okay, D. Tim dropped a coin off a bridge. It is falling at a rate of 9.8 meters per second. Keyword squared. What does that mean when you're squaring something?
Multiplying by 2
Not multiplying by 2, but multiplying it by
itself.
itself. So squared is actually a very important multiplication word. And we're going to get really good at noticing those multiplication words. So when you see a word that tells you to multiply, you know that's going to be exponential. So D is exponential. And then E, the amount of people in a stadium is decreasing at a rate of 45% every 10 minutes. So what do C and E have in common? Or B and E, sorry. B and E.
Percentage.
They both have percentages. And this brings me back to something that I think Chris mentioned a little while ago, which is investments. So looking at example B, Mr. Dominguez invested $1,000. This money is growing at a rate of 4% each year. When you invest money, it's always going to grow at a certain percentage. The higher the percentage, obviously, the better. But usually it's going to be a pretty small percentage, like 4%, that's pretty normal. And what happens is that it's not that you're adding the same amount every year, you're taking a percentage and adding it every year. And that is actually a special type of multiplication. So I'm going to explain it in just a second. That's a special type of multiplication. So anytime that you see a percentage, that is also going to be exponential. But let me show you what that means. So let's say I invest, just like Mr. Dominguez, I invest $1,000. But I'm going to make the percentage a little bit more. I'm going to make it 10%. 10% each year. What is 10% as a decimal?
Zero point 0.10.
0.10, good. So what this means is that what I'm going to do is I got to multiply this by 0.10 and then add that amount. So go ahead and you can use your calculator. What is 0.10 times 1,000?
100.
100, right? So I'm actually adding 100. So actually, let me just fix this. I'm adding $100. So the next year I have $1,100. But now what I got to do for the next time around is I'm going to do the same thing, but now I'm starting with 1,100. So now I got to figure out what is 10% of 1,100. Go ahead and use your calculator. 0.10 times 1,100. What do you get? We get 110. Good. So this time I'm adding $110. So I end up with $1,210. Well, now I'm going to do the same exact thing. This time I'm taking 1,210 and I'm multiplying it by 0.10. What do I get now?
$210.
By 1,210.
Oh, 121.
121. So I'm adding 121. So I end up with 1,331. Okay, so now let's talk about this pattern. My growth rate is 10%. So each year I get to add a little bit more. The first year I add 100, second year I add 110, third year I add 121, and that amount that I add grows over time. So even though at first it doesn't look like I'm making that much money, 10 years down the road, this account will probably have like a lot more money. It could, I don't know the exact number, but because it's exponential, we already know with exponential functions, they start out slow, but as long as you're patient, eventually they shoot up and they start to grow much more quickly. So percentages, big indication that you have an exponential function. Percentages are exponential. So now let's take a look at example 2. Take a look at example 2. Similar idea, we're going to see which of these are exponential. And I see a couple of people have already highlighted some important information. Does anyone notice? I see one more that I can highlight that's also going to be exponential. There it is. Good. So anytime you see a percentage, that's exponential. Even if it's decreasing, even if it's going down, that's still going down by a percentage. So that's still multiplying. And then what is the multiplication word for answer choice 5 or E?
To square,
But what's the actual word
multiply.
that it uses?
No, doubles.
Doubles. So there's another multiplication word. Okay, so long story short, exponential functions. Exponential functions. There we go. Fall into 2 categories. One category is anytime you see a percentage. And the other category is anytime you see a multiplication word. So can anyone give me some more multiplication words? Just to,
By.
okay, so the word by is a multiplication word, but you're not really gonna see it like in a word problem like this. So for example, doubles is a good one. What's similar to doubling?
Tripling, square.
Triple, square, cubed, anything like that, that's a multiplication word. So that's what you kind of got to look for with these types of problems. Look for exponents, look for percentages, look for multiplication words. Any questions on how to figure out one versus the other, exponential versus linear? Okay, so now let's take a look. I want you guys to do this one on your own. Think about it, read each question, each situation to yourself. Think about your answers for about 1 minute. And in 1 minute, I'm going to have you guys reveal the answers for me. So you don't even have to put it in the chat. Just think about it to yourself and have your answers ready. All right, so hopefully you have an idea of which one is going to be which. Now go ahead and I want everybody, as many people to do this because it's much more fun when more people do it. On the annotation toolbar, there is a stamp option. So everybody go to the annotation toolbar, and instead of text or draw, go to stamp. Don't do it yet. Oh my goodness, y'all, you gotta wait for my directions. Okay. In those stamps, there's a check mark, there's hearts, there's a couple of them. You can choose the check mark or the heart or whichever one you feel like, and go ahead and at this time, go ahead and put the correct answers on the board. As many people as possible. Go ahead and do it. Let's see if we all agree. Okay, that looks good, guys. It looks like we're in agreement. So this is correct. It looks like the correct answers were chosen. So does anybody have any questions on why those are what they are? Why is number 1, number 3, and number 5 linear, and then the other 2 are exponential?
I would probably just need like, if it's like a percent, it's probably exponential, and if it's not, it's probably linear.
Right, so percentages, exponential, for sure. And if it's not, then it's going to be linear because there were no multiplication words, there were no other indications that you have exponential growth. All right, so one last thing I wanted to just point out is the word interest. So remember what I was saying with money. Interest is a percentage. So I'm going to just write that down. With money, interest rate is a percentage that you gain every year. So in the previous example, when I was doing 10%, that was the interest rate. So if something has interest, then it's also exponential. So just look out that word, you can add that to your list as well. So interest is also exponential. Everything else happened to be linear. All right. Any questions, any final questions on linear versus exponential using a word problem? Awesome, awesome. Okay. Well, now what we're going to look at is, we know in math, sometimes you have word problems, sometimes you have graphs, and then sometimes you have a table. So we're going to pretty much spend the rest of class looking at these tables right here, because with tables, it's a little bit harder to notice when you might have a certain pattern. So one more time, remind me, linear functions, what operation are linear?
Addition and subtraction.
Addition and subtraction. Addition and subtraction, whereas exponential is, good, Daniela, multiplication. Multiplication. Okay, well, let's take a look, because one of these tables is a little bit easier than the others. Does anybody notice a pattern going on with any of these?
Yes, per C, it just increases by 1 million.
In C, it increases or decreases?
Oh, decreases.
Decreases. It's going down, right? We start with 24,000 and it goes down. So I have minus 1,000, minus 1,000, minus 1,000, and so on. What type of function is this going to be?
Linear.
Yeah, this one is definitely linear because it's going down by a constant rate of change. This is my constant rate, also known as the slope. Okay, because it's subtracting, so I know it's linear. Well, the rest of them, it's a little bit harder to tell, isn't it? These numbers are not that easy. They're not as simple to understand. So what we're going to do is now we're going to try and figure out what is the pattern that is going on. So what I'm going to do is we're going to do answer choice D. So let's just take a look at what's going on here. In order to figure out the pattern, actually, right now, everybody, calculators out, please. Go ahead, even if it's your phone. I'm using my phone because I left my calculator in my car. So go ahead and have your calculator out. And here's how we're going to figure out if it's linear versus exponential. So we're going to check to see if it's linear first. And the way to do that is you're going to go from the bottom. And you're going to take the bottom number and subtract the next number. So in your calculators, go ahead and plug in 13,057.23 minus 16,321.54. What do you get? What do we get? 13,057.23 minus 16,321. I know it's a lot of numbers, but go ahead and use your calculator. And you can put it in the chat or say it out loud once you get an answer. Good, Cassie. Negative 3,264.31. Well, that is, once you have that number, that's actually what you subtract to go from one to the next. So this is telling me that 16,321.54 minus 3,264.31 is how I go from one to the next. Well, now I can go backwards and keep going. So we're going to just do that over and over again to figure out what value is being subtracted each year. So go ahead and do the same thing. 16,321.54 minus 19,430.40. What do we get? Anyone? Just plug it in. Just plugging those into your calculator, and good, Cassie. Cassie, you should be an accountant. You got fast fingers. Negative 3,108.86. Okay, I know that this feels repetitive, but we're just going to keep doing it because we're trying to see if there's a pattern. So now pick the next two numbers, see what you get. And if you do those, go ahead and do the last two numbers and see what you get. And we're trying to see if we have a constant rate. All right, what do we get for the next set of numbers? Cassie, you got it. Negative 2,649.60. Okay, at this point, let's pause right here. Do I have a constant rate? Do I have a constant rate? Is it subtracting the same exact amount each day, each year? No, there is no constant rate. So is it linear?
No.
Nope, not linear. Well, let's check out A and B. So I can't determine if D is the right answer. I don't know yet. I know it might be D because it might be exponential, but I don't know. So now let's look at A and B. So what I'm going to do is I'm going to split you guys into two different groups. Group A, you're going to just do A, and group B, you're just going to do B. So listen carefully. Group A is going to be Ilse, JC, Zakaya, Chris, Jalea, Sophie, DeJuan, Philip, and Wenchley. You guys are looking at answer choice A and do the same thing. So start from the bottom, subtract, get a number, then do the next two numbers, subtract, get an answer, then do the next two numbers, and so on. Group B, listen carefully. Group B is Andrea, Tyresha, Ascanio, Andy, Cassie, Marion, Angel, Cole, and Daniela. So you guys are looking at answer choice B, and same exact thing. Look at the first two numbers, subtract, see what you get, then keep going all the way up. So we're trying to figure out if these are linear. All right, take about 30 more seconds. So what you should be doing at this time is just seeing what you get each time, and you're trying to see if it has a constant rate. Good, I'm seeing some answers, and those answers look correct to me. So let's go through it real quickly. So let's go to answer choice B. Answer choice B, something interesting is going on down here, right? What happens between those last three values?
Is decreasing with 1,000?
Yeah, so here it's minus 1,000, and here it's minus 1,000. So it looks like it's going to be fine, but what happens here?
It jumps.
Yeah, what's this one? Minus what? Who got that math?
2,300.
Mm-hmm. 2,300 what?
200 and
This?
4.
Okay. So all of a sudden, that's a different number. So already we can tell that this is not constant. Not constant. So it's not linear. Okay. And then what about in answer choice A? Do I have a constant rate of change?
No.
No. Does anyone want to give me just the first couple of values so we can see why?
From 22,000 to 19,360, it's subtracting by 2,640.
Mm-hmm.
Then from
Then?
19,000 to 17,000, it's minus $2,323.20.
Mm-hmm. And then the last one?
From 17,000 to 14,000, it's minus $2,044.42.
Good. So again, there is no constant pattern, so it is not linear. Okay, so what do we do now? Because we're trying to figure out which of these is exponential. So right now, I know that they're not linear, but now I have to check. I'm going to do a similar process to see if they are exponential. And it's actually very similar because with linear, it's addition and subtraction. With exponential, it's multiplication. So instead of subtracting from the bottom to the top, what operation should I try? What's the opposite of multiplication? What's the opposite of multiplying?
Dividing.
Yeah, it's dividing. So we're going to check by this time, we're going to do the same exact thing, but now I'm going to divide rather than subtract. So I go through it. Let's find out what I get. 13,057.23 divided by 16,321. I get 0.799. I'm going to write 0.79. Then I do the next two, and I'm always going to get this decimal, but that's okay. That's okay. That's what I'm looking for. I'm getting a decimal, and we're trying to see if I get the same decimal every time. 16,321.54 divided by 19,430.4. I get 0.84. So already, what do we notice? Is it the same?
No.
It's not. I'm going to do one more. I'm going to give it the benefit of the doubt. Maybe it's going to match a little bit later. When I divide 19,430 divided by 22,080, I got 0.88. So that does not have a constant factor. It does not have a constant growth rate. So it's not exponential either. So this one is not it. This is not our choice. So now, same groups, same thing, but this time we're going to be dividing, dividing. Same groups, group A and group B. Go ahead and look at your numbers. Now this time go from bottom up and divide, 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 and see if you end up with the same value. See what you get. And again, the group A is Ilse, JC, Zakaya, Chris, Sophie, Dejuan, Philip, Andrea, and Tyresha. Or no, and just Andrea. And then group B is Tyresha, Ascanio, Andy, Cassie, Marian, Angel, Daniela. So divide, 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 see if you get the same answer. Okay, a couple more seconds. All right. Starting with B. When I divide 15,036.8 divided by 16,036.8, what do I get? What do I get? 15,036.8 divided by 16,036.8. Anyone?
Miss, you get like 0 point, and it keeps on going. It's like
0
random.
point, 0 point what? Give it to me.
Oh, Miss, I give it to you. Okay.
Yeah.
0.937644342.
Okay. So I'm gonna round it to the nearest hundredth. So anybody can give me this answer. What would that be to the nearest hundredth?
0.4.
0.
9.4.
0.94. Good. So 0.94. Okay, what's the next one? 16,036.80 divided by 17,036.80. It's another long decimal, but what do I get? Going once. Going twice. Just read that number off your screens. It's not that hard. What do I get? All right, 0.9413035, but if I round it to the nearest hundredth,
0.94.
0.94. Y'all, give me my answers. Y'all are so quiet today. I don't know what is happening. Half of you went back to school and forgot how to talk. Next one, what do I get? 17,036.80 divided by 19,036, because right now it looks like it has a constant rate, but what happens in the next round?
It changes.
Yeah, what is it now?
I don't have a calculator, miss.
You have internet, go on Google.
But miss, those are big numbers.
I don't care, plug them in.
Thank you so much, Cassie.
0.88. Cassie, everyone's making you do all the work. That's not fair. Okay.
Everybody else has a calculator.
So this one, again, is not exponential because it looked okay to begin with, but in the end, we got a different number. So that brings me to answer choice A. And I know a few of you put it in the chat, but go ahead and say it out loud. What happens in answer choice A? What do I get when you round it to the nearest hundredth? What do you get each and every time? Okay, so Ilse, you got the same answer each and every time, right? You got 1.14 each and every time? Okay, which is good, except you did it backwards. So just be careful because you want to take the bottom number divided by the top number.
Miss,
So
I did that, but I thought it was wrong.
No, you were right. You were right. So make sure, because we're kind of we're doing it backwards in order to figure out what the pattern is going forwards. So when you go backwards, what do you get? What do you get? What was the pattern? And anybody can answer this if you had it.
It's exponent.
Good. So the pattern is, for example, on the very last one, you get 0.879, So when you round it to the nearest hundredth, what is it?
0.88.
0.88. Yeah. And as it turns out, you get that every single time. 0.88, 0.88, 0.88, on and on and on. This is not the slope. No, it's not called the slope. This is called my growth rate. So that means that this is exponential. Yes, it is exponential. So answer choice A is the one I'm looking for. So this is a long process, right? I told you guys we were going to spend the rest of class just looking at this one question because it takes a while to do all that math, especially when you have big numbers. But what's the big takeaway? What's the big takeaway? Going from bottom to top, what do you do to see if it's linear? Going from bottom to top.
Divide.
Subtract.
Subtract to see if it's linear, and then to see if it's exponential,
Divide.
divide. Exactly. And if you see a pattern, then you know that's what the function is. So since we got a pattern by dividing, I knew that this was exponential. Whereas answer choice C, we had a pattern from subtracting, so that one was linear. And then B and D were not linear or exponential. They were neither. So we kind of learned a lot today. I just want to very quickly, we didn't get to everything, but that's okay. We'll get to it later. Just quickly wanted to summarize everything that we've learned. So can I get 4 volunteers to read these 4 bullet points, and then we will be all done for today? What is special about exponential functions?
Can I read?
Mhm.
Growth or decay by constant factors, this is called growth rate, do not have a constant rate of change, will always exceed linear functions of can be written in form fx equals a times bx, where a is the y-intercept and b is the growth rate.
Perfect. And we didn't really get to this part today, but we will talk much more about that tomorrow. There is homework on Khan Academy. It's already there. It's 2 assignments, but I would wait until tomorrow to do them because what you learn tomorrow is going to help you, especially with the second assignment. You might be able to do the first one, which is a lot like what we just did. But if you want to take a look at them tonight, just to see what they look like, feel free to do that. Just know that they're not due until Friday, so you do have a little bit of time. All right, everybody, that is all for today. Have a happy and hopefully not too rainy rest of your days. I know that thunder's kind of getting crazy, so everybody stay dry. See you all tomorrow.
Bye.
Bye.
Also, Miss,
Bye.
did